Okay, the tests, I'm about a third of the way done with the night class, so I'll definitely have them done sometime, probably Friday, I suppose. That's my best guess. The grades will be posted Friday, and I'll have them back to you on Monday. Is my plan. Yes.
And then we all take the lab exam in class on Monday?
Oh yeah, good question. Yeah, let's. Lab exam 1 is in lab next week. So you can, the idea is you go to your lab. Like always, you can go to whichever one makes sense for you, Monday or Wednesday. But just instead of doing a lab, we're going to space out as much as we can in the lab room. Actually, now that I think about it, we're probably just going to do it in here since it's open and it's the easier place to take tests. But
during your assigned...
During the lab period, right. And so there have been 3 labs, and so the questions will be like the questions from the 3 labs. Those are distributions, position versus time graphs, and the one for this week, air resistance. And all of those labs are posted on D2L, so you should look at those labs, remind yourself how to do those problems. The problems on the lab exam will be very similar. Yep.
With distributions, will we have to know the standard deviation formula?
No, I'll give you the formulas,
Okay.
but you have to know how to punch it in, and I'll probably make you punch it in for a small number, say like 5 data points or something, not 30 or whatever. The whole test is just calculating a standard deviation of like 150. That's a good idea. Okay, so think back to when you took the test. You know how the test, think about how the questions on the test, how similar were they to the practice problems, That's about how similar the lab exam questions are going to be to the labs, I think you probably would agree they're quite similar, It's the same thought process, and that's the idea with the lab exam, too. You just have to know how to do those kind of questions. Okay. Any other questions about the lab exam? All right. Well, we are done with particle kinematics. Along a line. And now we're going to particle kinematics in 2 dimensions. And one way you can think about it is along a line, all directional quantities those directional quantities are position and displacement, but I'm just going to write it as position, velocity, and acceleration. Had a magnitude and second, a direction. The direction was given by the sign, you know, whether it's positive or negative. And that was possible because if an object's moving along a line, it has two choices at any location of where to go. And 2 happens to be exactly the number of signs that are available. So you can assign 1 to one direction, 1 to the other direction, and that gives you all the information you need to know about direction. In 2D, the idea is similar. Position, velocity, and acceleration have a magnitude and a direction. But this time the sign doesn't give us enough options to, you know, to specify a direction.
Sign doesn't want enough options.
Doesn't give. 1, that does look like 1. I'm not changing, you have to change. Doesn't give enough options to specify the direction. And here's why. Because in 2D, at this location, the object can go there or there or there or there or there or, you know, anywhere in between. There are infinitely many choices of direction. Okay, so that's why we need to define this new directional thing. A number, a positive, negative number, won't cut it anymore. We need to define a new mathematical object that possesses direction, that has direction. And that object is called a vector. And so think of a vector as an arrow in space. Okay, so that's a vector. And this vector has 2 properties. A magnitude that's given by the length of the arrow. And a direction that's, you know, given by where the arrow is pointing. Where it's pointing. Once you choose a coordinate system, you can define a vector numerically in terms of its components. So you can define a vector numerically by its, no apostrophe on that kind of its, components. So let me show you what components are. So if this is your vector, and this is your coordinate system, and I'm putting the origin of the coordinate system at the tail of the vector, that's not a coincidence. That's what we're going to do over and over again. Then the components of the vector are how far you have to go along the x-axis, followed by how far you have to go along the y-axis to get from the tail to the head. So this is called the x component. And the blue one's called the y component. And notice that these two are perpendicular to each other. And the reason that we're going to always express vectors in components like this is it's easy to do math with vectors once you break them up into components. So the idea of the vector is the arrow thing, but mathematically we're going to always represent a vector as components. Okay, so how do you find a vector's components? So the first thing you're going to do is, so when I talked about what properties a vector has, I never said anything about its location, right? All I said was its direction and its magnitude. So we can move its location anywhere we want. And so we're going to start by putting the tail of the vector at the origin of the coordinate system at 0, 0. Then the second thing we're going to do is figure out the counterclockwise angle. I'll do an example to show how to follow these steps. But the counterclockwise angle from the positive x-axis of the coordinate system to the vector. And we're going to call that angle theta. Greek letter theta. That's a lowercase theta. Then the vector components are, and I'm always going to write vectors, so I just have V for vector. This is just some arbitrary vector, but I'm going to indicate a vector with an arrow over the top, and its components are equal to L times the cosine of that angle theta, L times the sine of that angle theta. I'll talk in a second a little bit about what cosine and sine mean, but in a way you don't even have to know. Cosine and sine are just buttons you press on your calculator, and your calculator does it for you, you know.
What is L?
L is the length of the vector. Okay, so let's say that we have a vector let's say we have a vector that makes an angle of, what does that look like, 70 degrees? 70 degrees with the horizontal, and has a magnitude, a length of 5. Okay? And let's say our coordinate system is oriented, well, actually, let me hold off on that. And we want to figure out what are the vector components
Did you say the counterclockwise angle?
Yes. So that, right, so that's not going to do it.
Okay.
But that's going to let us get there. What are the vector components in, first, this coordinate system, the one we're used to, where the x-axis points this way and the y-axis points that way? And then second, what about a coordinate system where the x-axis points up and the y-axis points to the left? Okay? Coordinate system. Yeah. They don't have units yet because these are just mathematical things for now. But these are going to represent position, velocity, and acceleration, and displacement. And so they're going to, if it's a velocity vector, it'll have units of meters per second. If it's a position vector, it'll have units of meters, like that. But for now, they're just mathematical things. Okay, so Part A. Part A! That was stupid. Okay, so we're going to put the tail of the vector at the origin of the coordinate system without changing the orientation of the vector. So the vector goes like this. Okay, and we still know that this angle is 70 degrees. And we know that the magnitude of that is 5. The length is 5. So that's step 1. Step 2, we have to figure out how far do you have to go counterclockwise to get from the positive x-axis to that vector. Well, it's each time you go each time you go from like one axis to the next, it's 90 degrees. So you can think of it as 90, 180, but then we didn't make it to this one, so we have to backtrack 70. So it's 90, 180, minus 70, 110. So theta is equal to 110 degrees. And so that vector in components is equal to 5 times the cosine of 110, 5 times the sine of 110. You have to make sure, we're always going to use degrees instead of radians for angles. So you need to make sure that your calculator is in degrees. Let me know, I can help you do it if you can't figure out how to do that. But this is 5 times cosine of 110 is negative 0.171, 1.71, I think. And 5 times the sine of 110 is equal to 4.7. And so those are the vector components. Yes?
Where did the 5 come from?
That was given in the problem. I said that the vector has a length of 5. Mm-hmm.
And so that's negative 1.71 in the x direction, 4.7 in the y direction.
That's right.
Not 1.71 over.
Yeah, you can think of it as to get from
No,
here to
I mean
here.
like divided by.
Oh, right, not divided by. Correct. Those are two separate numbers. Yep. And so what that's saying is that to get from the origin to here, you have to go 1.71 in the negative x direction, and then you have to go 4.7 in the positive y direction. And this component form is mathematically how we're going to treat vectors. Any other questions about that? To get, we have to go, what this is saying is we're going 1.71, negative 1.71 in the x direction, or 1.71 in the negative x direction, and then 4.70 in the y direction to get from the origin to here, to the head, to get from the tail to the head.
So are you essentially finding the coordinates of the head?
Yes, that's exactly right. So I'll write that down after I finish the second example, but that's exactly right. It's totally equivalent to finding the coordinates of the head once you put the tail at the origin. Okay, so part B. So now we have this new coordinate system with the x-axis up and the positive y-axis to the left. So that's x, that's y. The vector doesn't change. So the vector still, it's independent of our choice of the coordinate system. It still just lives over here. Okay? And it's still 70 degrees from the horizontal. And it still has a length of 5. So now what angle? We want to go from the x-axis to the vector, but the x-axis is in a new place. The vector is still in the same place. How far do we have to go from the positive x-axis to line up here? 20. 20, yep. You can think of it as 70 plus 20 add up to 90, or you can think of it as go 90 and then backtrack 70. But theta is equal to 20 degrees. And so in this coordinate system, the vector components are 5 times the cosine of 20. Five times the sine of 20. And that is 4.70, 1.71. In this notation, that top value is called the x component. That's how far you have to go in the x direction. And the bottom one is called the y component. Okay, so notice that finding the vector components is exactly equivalent to finding the coordinates of the vector's head. And so based on that, you can use that idea to sanity check your components. If you break it up, if you break the space up into first, second, third, and fourth quadrant, you know that, like for example, that's the first quadrant, second quadrant, third, this is with x there, y there, and fourth. You know that your components for a vector that's in where the head is in this quadrant have to be positive, positive. Bless you. The second quadrant has to be negative x, positive y. The third quadrant has to be negative x, negative y. And the fourth quadrant has to be positive x, negative y. Yeah, so in that case, yeah, in that case, this is the first quadrant. And then this is, yeah, because it's second, third, fourth, and then it makes sense. Yes. Yeah. Uh-huh. Why don't I write it on that other one too while I'm at it? So in the first example, first, second, third, fourth. Mm-hmm. So this isn't really necessary for anything in this class, but since we're going to be using sine and cosine a lot, let me just go through a definition of what sine and cosine are. So this is the definition of, I'll say, cosine and sine. This is not for this class, it's simply for your personal edification. So draw a coordinate system. And draw a unit circle that's a circle with a radius of 1. Centered at the origin. Okay. And now draw a line from the origin out to the circle, wherever. And take the counterclockwise angle from the x-axis to the line. I'll call that theta. So that has the same meaning as that theta for the vectors. So theta is the counterclockwise angle from the positive x-axis to the chosen line then the cosine of theta is the x-coordinate of that point on the circle. So the point we're talking about is here, where that chosen line meets the unit circle. And the sine of theta is the y-coordinate of that point on the unit circle. So based on that, if the radius of this circle is 1, what's the cosine of, so if we don't go anywhere, if this angle theta is 0, we're talking about a red line that's along the x-axis. And so the cosine of 0 is the x-coordinate right here. What would that be? 1, yep, because the radius is 1. And what's the sine of theta is the y-coordinate of that point. What would that be? 0. And then if theta is equal to 90 degrees, imagine that red line going straight up. The cosine of 90 degrees is 0, the x-coordinate of that point.
0.
What did I say?
You said the x-coordinate.
The x-coordinate is 0, right?
Yeah.
And then the sine of 90 degrees is the y-coordinate of that point, and what would that be? 1. Okay, let's do both of the other two. So now if theta is 180 degrees, the red line is like this. So we're talking about the coordinates at this point. What's the cosine of 180 degrees? Negative 1. What's the sine of 180 degrees? 0. And then down here, you can think of that as the cosine of 270. Or you can think of it as going the other direction. You call it a negative angle. So the cosine and sine of 270 or the cosine and sine of negative 90, it'll give the same thing. What's the cosine of 270? 0. What's the sine of 270? Negative 1. Yep. And then your calculator will let you fill in all the, any angle in between those values. Anybody have, that was quick, but anybody have any questions about that? Okay. So once you have vectors expressed as components, you can do math with them. Let's say you can perform mathematical operations on them. And the ones that we're going to do are, I'm going to talk about adding two vectors. I'm going to talk about multiplying a vector by a number. And I'm going to talk about calculating the magnitude of a vector. Okay, so the first one is adding two vectors. So if you have a vector AB, so A is the x component and B is the y component, and you're adding it to a vector CD, the answer, the resultant vector, is equal to A plus C for the x component and B plus D for the y component. So if you have, if you're adding the vector 5, 3 to the vector 6, negative 2, for the x component of the sum of those vectors, it's just 5 plus 6, so 11. And for the sum y component, it's 3 plus negative 2, so 1. This sum, by the way, is called the resultant vector. The second thing we're going to do is multiply a vector by a number. So if you have a number k and you're multiplying it to a vector AB, the vector you get out is k times A for the x component and k times B for the y component. So, for example, if you're multiplying the number -3 times the vector 2, -4, the vector you get out is -6 for an x component and +12 for a y component. Any questions about either of those yet? And then the last one we're going to do is calculate the magnitude. So sometimes we'll start out a problem knowing the components, and we'll want to use those components to figure out the magnitude. The examples that we've done so far, we've started out with a magnitude and used that to calculate the components, but sometimes you want to go the other way too. So if you have a vector u that's equal to AB, then the magnitude of that vector, you write it like it's the absolute value. So this is how you write magnitude. Is equal to a squared plus b squared all square root. Does that expression look familiar to anyone? Yeah, that's the Pythagorean theorem, and it makes sense that to figure out the length of the vector, you'd use the Pythagorean theorem, because if you go back to, go back to the original vector that I drew. The x component is the plus or minus length of this leg. Like you can think of this as a right triangle with the hypotenuse being represented by the vector itself, one leg being represented by the x component, one by the y component. And the Pythagorean theorem says the length of the vector, that's the length of the hypotenuse, is equal to square root of this squared plus this squared. So it is the Pythagorean theorem, and that's the connection. So, for example, if you have a vector u that's equal to -3, 4, the magnitude of that vector is -3 squared plus 4 squared square root, which is square root of 25, which is 5. Yes, the top one is X and the bottom one is Y. Okay, so mathematically, that's how we're going to, those are the operations we're going to use with vectors. But if you think of vectors as arrows, these operations also have physical meanings. So let me describe what the physical meanings are of these three operations. Physical, I don't know, that might not be the right word, but intuitive kind of, like what does it mean to do these things? The physical meanings of these operations. So the first one is adding two vectors. So to add two vectors, put the tail of one vector. The order doesn't matter, so it can be either one. Put the tail of one vector at the head of the other. Then the resultant vector goes from the free tail to the free head. All right, so if our two vectors are this, and we're adding it to this, then what we get is, I thought I was going to be so cool. Well, what we get is, so we'll take one of these, put it there, put the tail of the second one at the head of the first one. Then the resultant vector goes from the tail that doesn't have anything, where there's nothing there, to the head where there's nothing there. So the resultant vector is this. You can do it with either order, so you could also, I could have done it as this one. Put the tail of the red one at the head of the first one. And then draw the resultant from the free tail to the free head. And notice those two resultant vectors are the same vector. So the order doesn't change anything. Okay, so that's the interpretation, and it's kind of just a surprising fact that this physical meaning corresponds mathematically exactly to that thing where you just take the components and add them together. You know, but that's what it does. Any questions about that, adding two vectors? And then for the meaning of multiplying a vector by a number, vector keeps its direction and its length is multiplied by the number. A negative number means the head and tail switch ends. Okay, so if we're going to multiply -2 times this vector, the meaning of that is you multiply the length by 2, so now there's 2 of these, but it's negative, so it's the length of 2 of those, but now instead of the head being down, the head is up. Any questions?
Can you explain that one more?
Yeah.
So, I know the -2 go down because it's negative.
Right.
And then the length, why did we switch it? Just because it's negative, so we know that it was switched?
Right. So first, so you can think of it as do it in 2 steps. We're multiplying by 2, and then we're multiplying by a -1. Multiplying by a negative. So first multiply it by 2. That just you double the length. So now it's this. And then apply the negative, and so instead of going this way, this far, we switch the head and the tail, and we go this far, that direction.
And then that's our resulting function?
The resultant only refers to adding, so I don't know what you call this.
So because you basically multiply the negatives by a negative, you keep it positive,
The what?
that you got a positive, you multiply
In
the
the
vector by,
numeric.
yeah, is that why it would be positive? For the number 2,
Back here?
yeah, the last example you just did.
Yes. Right. I mean, whatever like when you're doing these calculations, it just follows the rules of multiplication. So we have -3 times 2 gives you -6, and -3 times -4 gives you +12. Any other questions? Okay, so now let me say 2 things about coordinate systems. To fully specify a coordinate system, you need to make 2 choices. First, you need to choose an origin location. And second, you need to choose the axis orientations. You know, how the coordinate system is tilted. Choosing the origin location is the 2D equivalent of choosing the 0 position. And choosing the axis orientations is the 2D equivalent of, what do you think? Of choosing the positive direction. Yep, exactly. Bless you.
Can you put the axes on like a jaunty angle, or does it always have to be like 90s?
No, you can put it, yeah, you can be as stylish as you want.
Alrighty.
There'll be times, I guess there'll be one topic that we'll do where we're going to put it at a funny angle always. But that's what the second, so this is the first thing. 2 things, that's the first. And the second thing is, what are the rules for coordinate systems? Like, can the x-axis be curly Q? No. So the rules for coordinate systems. And the rules are, first, the x and y axes have to be perpendicular. And second, it has to be, we're only going to allow rotated versions of what we can think of as sort of like the standard coordinate system, the one we're most used to. They can't be flipped over. So if my thumb is the x-axis and my finger is the y-axis, all of these are allowable orientations, but that's not. Okay. So, for example, this is okay. But this is not okay. Because there's no way to start with this and rotate it to get this. At some point you have to flip it over, and that's what's not allowed. Okay, so where we're going now is the things that are vectors in 2 dimensions and in 3 dimensions. We're just not going to do those kind of problems. Are position and displacement. We won't use that as much. Velocity and acceleration. So position, velocity, and acceleration are all vectors in 2 dimensions. So let's think about the definitions of those things. And you'll see that the definition is, it follows the same kind of line of thinking that it did in 1 dimension along a line. But there's some things that have to be changed. So let me first define the position. So along a line, I did this as a train. But a train has to stay along the tracks. This doesn't have to anymore. So I'm going to put wings on it. So, yeah, it's a flying train. And what did we have to do? We had to choose 2 things along a line before we could specify a position. What were those 2 things? Do you remember that? Yeah, we had to choose a 0 position and a positive direction. So now what we're going to do is choose a location for the origin and choose a coordinate system orientation. So X and Y, and I'm going to call the train's location its center of mass. I think that's what I did before. And so now the position vector is a vector that goes from the origin of the coordinate system to the object. And so if the length of this vector is L, and the angle from the positive x-axis to the vector is theta, then the components of the position vector are L times the cosine of theta, L times the sine of theta. The units for position don't change in 2 dimensions. It's units of length. And so the SI units are meters. And then the way we defined velocity for motion along a line was we first defined the average velocity based on positions at 2 instants. And then we pinched those 2 instants closer and closer together until they ended up representing a single instant. Remember that vaguely? So for velocity, choose 2 instants. T initial and T final. Then the average velocity vector is equal to 1 over T final minus T initial. So that's a number. times the velocity vector, the position vector at time final minus the position vector at time initial.
So subtracting vectors is similar to adding them.
Yeah, subtracting vectors, you can think of it as you multiply the second one by -1, and then you add those.
So is that position times time final?
No, that's position as a function of time final. Position at time final. So that's the position at instant time final and the position at instant time initial. And then the if you pinch TI and TF closer to an instant T, that defines the instantaneous velocity as a function of time. Okay, so this is the instantaneous velocity. That's the one we're going to care about. The units for velocity are length per time and so the SI units are meters per second. And then the last one we have to define is acceleration. And so for the acceleration, choose two instants TI and TF. Then the acceleration vector is equal to 1 over TF minus TI times the velocity vector at TF minus the velocity vector at TI. The units for acceleration are length over time squared and so the SI units are meters per second squared. And we're going to end up basically using the same equations we used for motion along a line. So the 2D equations for constant acceleration, constant acceleration kinematics, we had 3 for motion along a line. Now we're going to have 6. And they're going to look exactly the same, but we're going to have an x component equation, a y component equation for each one of those 3. Okay, so I'll write it as the first equation has an x component that says Vy is equal to, V final y x. Okay, that's the last mistake I'm going to make today. V final x is equal to V initial x plus AX times TF. And then the y component equation is exactly what you would think. Just replace all the x's with y's. V final y is equal to V initial y plus AY times TF. The second pair of equations, the x equation says PFX is equal to PIX plus VIX times TF plus 1/2 AX times TF squared. And the y equation says PFY is equal to PIY plus VIY times TF plus 1/2 times AY times TF squared. And then the third equation, the x version says 2AX times the quantity PFX minus PIX is equal to VFX squared minus VIX squared. And the y version says 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So the x's and y's and all these refer to the components. And so if you know the components for position, velocity, and acceleration, you can use these equations to find values of components that you don't know, or to find time. So notice that the one thing that doesn't change from motion along a line to two-dimensional motion is time. There's no vector time. There's just time. Question?
With regards to the 3 mathematical operations concerning vectors that we did before, why would you do that with the vector in physics?
Why would you do it?
Yeah. Like, why would you multiply by a scalar for
Yeah.
the velocity?
Well, I think maybe the answer is, for us, we're not going to do that.
Okay.
I think that might be the answer. I'll have to think about that, though. But you use those operations to come up with these 6 equations.
Okay.
But then I didn't go through the derivation anyways, so I don't know. Maybe it'll come up. I'll have to think about that. That's a good question. Yeah. You can also, using those operations, you could define these equations in a way like this. Like you could just say VF as a vector is equal to VI as a vector plus the vector A times the scalar, the number TF, you know. And then the vector operations give you those 2 equations that I gave you. Any other questions? Okay, we're like so close to being able to actually do problems. That was just like a lot of talking with no payoff. But the payoff comes Monday. I'll go get them. Okay, that's all.